Hello, my name is Cenk Feridunoglu. I'm happy to present in Case 20 virtual conference. I'm the Director of Engineering for Empower Operations. Our flagship product is Oasis, an AI machine learning based optimization software. Today I'm going to talk about the importance of constraint handling for optimization performance. I have 6 sections in my presentation. I will start with design optimization basics and continue with constraint types, optimization cycle. Then I will introduce a new optimization algorithm called SAX-TRO and benchmark results. Lastly, I will present benchmark results for Oasis. I would like to start with a quick recap of design optimization, which is a structured search of better performing designs by changing selected inputs. Design performance is measured by computer simulations of FEA, CFD, electromagnetics, or other types. Here at the left-hand side, there's the formal mathematical form of single objective optimization, where there's an fx function to be minimized, which is the objective, and that corresponds to simulation output or CAD properties in a simulation-driven optimization, where CAD properties being mass or volume, simulation output, depending on the simulation type, it could be stress, displacement, velocity, or gain. And then this minimization problem is subject to H and G functions being the constraints. H being the equality constraint and G being the inequality constraints. And these constraints correspond to important design criteria that can involve input variables or outputs. And lastly, we have X, which is the value of our input variables defined with min and max values of bounds, which creates our search space. Let's have a look at a simple example of parametric CAD and simulation-driven optimization scenario to draw the line between cheap versus expensive constraints. Here we have a simple rotating component, and I would like to find the minimum mass by changing the slot width, height, distance from the center, and number of slots. I want to preserve the shape of the disk within the given input variable bounds. And the first constraint I write to control the vertical movement of the slot is vertical length from the center of the slot tip should not exceed a certain value. If I do not apply this constraint, which is this one here, if I don't apply this constraint, then the slot might cut the disk perimeter, which is a case shown in drawing A here. And the second constraint is controlling the slot width and the number of slots so that the slots do not interconnect and cut the center hole. This is my second constraint to control the width of the slots and the number of slots. And if I don't control it, they might interconnect and cut the center hole, which is an invalid design. So the two constraints we went through only require input variable values to be calculated, which makes them computationally cheap. The third constraint is an important design performance criteria, which comes from a baseline design. It is expressed as stress maximum less than a certain value, which is coming from the baseline design. So this constraint here is an expensive constraint because it is dependent on a simulation output. Here's a typical optimization cycle to to see when and where an optimization software sets and gets inputs and outputs. Here we have a typical setup and the optimization software at the center button, which is Oasis in this case, to drive the cycle. The left hand side we have the inputs and the cheap constraints. The cheap constraints should be satisfied before the simulation call. And the simulation can be a combination of CAD, preprocessor, and solver, or a commercial package which does all. But the essence here is the cheap constraint is already satisfied before the simulation call. Then the simulation takes place, which can take half an hour to 12 hours or even more depending on the setup, and the outputs are released at the end. Based on the outputs, the optimization software calculates the expensive constraint values, and any design that do not satisfy a constraint is marked as infeasible. So there's no prior knowledge of expensive constraint values, which makes constraint handling technique critically important for the effectiveness of the optimization study, especially for high-dimensional and highly constrained problems. As I mentioned on the previous slide, if a set of input variables, a design, violates at least one of the constraints, then it is labeled as an infeasible design. And here is a 2D hypothetical representation of a feasible region in a search space. And what we expect from an optimization algorithm is to start the search and move into the feasible region and find a better performing design in a reasonable simulation call budget. In other words, time. And the question is, how effectively an optimization algorithm handles the expensive constraints, which is the boundaries of the feasible region, to find its location, especially for challenging high-dimensional and highly constrained optimization scenarios. Current situation. Most of the commercial optimization algorithms on the market require impractical number of simulation calls or cannot find a single feasible design for highly dimensional and highly constrained problems due to lack of novel, expensive constraint handling methods. A new optimization algorithm called SAXTRO, which is published in June 2018, it utilizes a meta-modeling-based global optimizer with an adaptive aggregation strategy to model active constraints dynamically throughout the optimization run. Here are the tabulated results of 9 different benchmark functions with number of inputs ranging from 3 to 30 and number of constraints ranging from 3 to 29. SAXTRO results are compared with 5 different optimization algorithms. CONMIN utilizes method of feasible directions for linear and nonlinear constraint optimization. SDPen has a derivative-free sequential penalty approach for nonlinear constraint optimization. KSOpt converts constraint problem into an unconstrained one and envelopes objectives and constraints. Cobila is a derivative-free approach that models objective and constraints with linear approximations. ALPSO is an augmented Lagrangian particle swarm optimizer that utilizes augmented Lagrange multiplier approach to handle constraints. There are 9 problems, and every problem ran 30 times with each optimization algorithm. And here I present the mean values for two important metrics to demonstrate the efficiency of the optimization algorithms, where less is better for both and highlighted with green. The first metric is number of function evaluations to get the first feasible design, which is the lower left table. SAXTRO is fastest to find first feasible design for all benchmark problems except the beam problem, where KSOpt was able to find a feasible design only at 2 runs, where their mean value of number of function evaluations are 19, where SAXTRO was able to find the first feasible design in 30 runs, and the mean value of the number of function evaluations are 20. The second metric is number of function evaluations to find target objective value. In the upper table, where I present the properties of the benchmark functions, the last column is the target objective value, which is a known objective value. And when we look at the results, SAXTRO finds target objective value for most of the optimization benchmark problems, except for P113 and P117. Cobila outperforms SAXTRO, and for the beam problem, SD-PAN outperforms SAXTRO. And more detailed benchmarking results are presented in the reference paper that I took all the results, which is given at the bottom of the slide. An enhanced version of SAXTRO algorithm that I presented in the previous slides is commercialized in Oasis software as a one-click optimizer. To demonstrate the Oasis performance, here I present you the P113 benchmark problem, which is implemented as a PowerShell script. And I show you the optimization setup here to better showcase the inputs and outputs. So the P113 is a 10 input variable mathematical function with 8 constraints. Whenever Oasis calls the PowerShell script with the value of 10 input variables from the given input variable bounds, the PowerShell script outputs the value of fx and the value of g1 to g8, which are the expensive constraints, and they should be less than 0. And we are minimizing the value of fx. You can also think about this P113 function benchmarking problem as a multidisciplinary simulation scenario, where this fx and g1 to g8 are a black box. Here we are looking at one of the runs of P113 benchmarking function with Oasis. So the upper plot is the value of input variables, where I only plot x8 just to keep things simple, and the x-axis is the number of simulation calls or function evaluations. This is a run with a budget of 250 function evaluations. And the center plot is the value of expensive constraints. Any expensive constraint value greater than 0 is a violation, and that design is considered as an infeasible design. And the lower plot shows the objective value fx, where the blue dots indicate an infeasible design, which means at least one of the constraints are violated, and the orange dots indicate the feasible designs. So in the beginning of the optimization run, there's an initial sampling here, and here you can see there's a big scatter of expensive constraint values. There are many violations. And as the function evaluations are progressing, Oasis sets a value for x8, and keep in mind this changing of input variables are happening for all input variables. For all the remaining 9 input variables, they've been changed by Oasis at every function evaluation. And before 50th iteration, as you can see, we have a couple of feasible designs, and the expensive constraint values are much more stabilized compared to the beginning of the optimization run. And Oasis has the feature we call this intelligent sampling redirection, where Oasis is learning from inputs versus outputs and treats these simulations or this PowerShell script as a black box function. And based on this inputs versus outputs, it is redirecting its search to the feasible region. And as the function evaluations are progressing, as you can see, the value of x8 is gradually moving from -10 to +10. And here at 100 function evaluations mark, we have many feasible designs, and the general trend of objective value is going lower and lower. And around 118th iteration, Oasis finds the global minimum for this benchmarking problem, which is a value corresponds to 24.18. And this very same benchmarking problem is utilized on the previous published paper of Sachs TRO, where the target value was 40. So the enhanced version of Sachs TRO is faster to find the feasible region and the global minimum. Here we see the all input variable values for the same run that I presented on the previous slide for P113 benchmarking function. And here you can see that we named it intelligent sampling direction is happening for all input variables at every function evaluation call. And here you can see this big scatter in the beginning, which is the initial sampling. There's a big scatter for the expensive constraint values, but after that things get rapidly stabilized on the expansive constraint values. And if you look at the lower plot of the objective value, we have many feasible designs before the 100th iteration mark, and around 118th iteration, somewhere here, we find the feasible design of the global minimum. For the rest of the iterations, Oasis is just cruising through the active constraints to find a better minimum. Here we're looking at the convergence plot for the same benchmarking function, P130, for 3 commercial optimization softwares, Oasis and other 2 commercial tools. And this plot is only showing the feasible designs with the objective value less than 100. The x-axis is the number of function evaluations and the y-axis is the objective value. And we have some metrics to be able to understand the performance and effectiveness of those optimization tools. The first one is the first feasible design and number of function evaluations. So less is better for this metric, and Oasis is 23. The other one is 113 and 138. What practically this means is the other tools require 5 to 6 times more simulation calls, meaning more time to find the first feasible design. And then the second metric is number of feasible designs. This is also an indication of how well the optimization software is exploring the feasible designs. So higher the better, we can say, because more feasible designs, different design configurations will appear. So Oasis has 229. The first one has 276 and the second one is 155. So the first one is higher number of feasible designs compared to Oasis, where you can see from there its blue convergence graph, there's a values of very similar, very close values of designs, feasible designs being found. Then the value of the optimum. So less is better in terms of the optimization performance. So 24.3, 26.28, 24.61. So less is better, and Oasis has found the best optimum value. And then the last metric is the optimum found at which number of function evaluations. And this is a run with a budget of 1,000 evaluations. And Oasis finds the optimum value at 596. The other tool requires much more evaluations. The first one is 999, the second one is 722. But if we look at the convergence graphs, actually the algorithms, the Oasis, is in that landscape of optimum nearly around 150-ish number of function evaluations. The first one, the blue curve, is in the same landscape around 350 evaluations. And the second algorithm, the red one, Never gets close to that, but maybe around 720s. So this is an indication of the constraint handling, novel constraint handling methods inside of Oasis optimization algorithm. So after all those benchmarking functions, here is a real-world example, which is called MOPTA-08, a multidisciplinary mass minimization problem from GM, which has 124 variables and 68 expensive constraints. So the input variables are various thicknesses from the car body, and the expensive constraints are outputs from various vehicle simulations, front, side, and rear crash, noise and vibration, and drivability simulations. So this problem is based on a real automotive problem and one of the most challenging and tightly constrained problems. Here we are looking at the convergence plot for the MOPTA-08 problem. And the smaller plot here is from a published paper by Regis, where various algorithms, optimization algorithms, are used to solve this problem. And the bigger plot is the convergence plot for Oasis, running the same problem, MOPTA-08. The x-axis is the number of function calls or function evaluations. The y-axis is the number of the value of the objective. And this solid line here is the aggregate curve of the best points from the smaller graph, which is published by Regis. And this problem is run 10 times with Oasis. And here the results are presented as the candlesticks. So we have the maximum and minimum and the median value. And this problem has a simulation budget of 2,000 simulation calls. And as you can see, the objective value of Oasis at every level of function evaluation calls is better compared to the aggregate curve or line of best points from the published paper. You can see the median values are always lower than the aggregate curve throughout the iterations. And this is a 124 input variable with 68 constraint car body minimization problem. To conclude this presentation, I would like to recap on the importance of expensive constraints, where they are a way of building optimization setups that effectively search for a better performing design than a baseline or a design criteria. And also, novel methods of expensive constraint handling could bring great efficiency in terms of feasible designs, the optimum values, and tight simulation call budgets, especially for challenging high dimensional and highly constrained optimization problems. Thank you for your attendance, and questions welcome.